Hi everyone, this is the lecture class of green engineering that I'm just trying to promote, and we'll start with the story of fluids. So basically, in this course, what we are going to cover, this is mostly following the syllabus from IITs or NITs in India, and also what are the competitive exams we have here in India. However, this is quite generic kind of syllabus where we take up the very basic sections of this science and technology. So let me start just answering the things that why we have another online class, because there are so many institutes are teaching this kind of subjects, and we are having so many online tutors also. So what I thought about sharing this my teaching experience in IITs for last 5.5 years, and also some stopgap teaching in US, that somehow what we are teaching in regular classes that may not be enough to capture the essence of the subject, and also kind of make the students be prepared for kind of larger applications. So what we have been facing during this climate change era, that we are see increasing temperatures, uh, varied uh, rainfalls, also the big floods around the world, and these are kind of pushing us rethinking about our strategies. And since we are rethinking is better, that we should start from our basics. And this thinking may be a very big thing, like maybe is kind of strategies, policies, and kind of new approach to the problems. But when we try to solve a problem, we have to go back to the basic again. So maybe like most of us may not get that time as a professional to go back to the basics. The teachers have that opportunity. They go back to the basics before the class, before any session, or kind of advising or professing to the students. So we have that option that we can go back to the basic to kind of find out a solution, a practical solution. So, in order, in that case, why we should not revisit those courses that we have, just keeping in the mind that all not only the students but also the practitioners who are there in the industry, or uh, in the different administrative positions, they also can get a chance to revisit the basics. And here, definitely, we are not sticking only to the formulae. Formulae are important, definitely. These are very important because we structure the whole science based on those formulas. We have basic theories, basic form, assumptions, basic hypothesis. So these we have to follow. But unless you understand the concept behind, just remembering a kind of mathematical expressions, that is not a good thing. Like what I have realized, like teaching in IDs for last 5 years, I have seen students who were there in the basic classes previous semester, and when they come back for maybe the lab classes or the sessional classes for the same theory, they almost forgot everything. Almost. If the somebody has didn't get an interest in that. So that is a kind of point that we should focus on when we go back to the basic for solving a problem. So we have to create the interest. And as you know, like when we listen to the stories, reading books, something interesting is very, very catchy things. And that particular part of the story we remember for long, maybe for entire life. So even we teach a very kind of basic engineering course, why we cannot combine that? So if we talk about stories, there are many stories are there, but if you start telling the stories in a class, that maybe you are not able to cover the syllabus. So there are subtle things that we have to kind of cater, or something we need to modify, where we can insert the stories in between the theories. So when we talk about fluids, always we talk about the properties, then fluid statics, fluid dynamics, how the fluid flow. So one point to another point. So we have Euler regime, we have Lagrangian region, and we have the mass conservation theory, we have the momentum equation, we have energy equations. So all are there, they are now established. But if you think of kind of history, when there were nothing much we knew, we didn't have these equations. Then also people find out solutions. Okay, and that's why I just mentioned about the Babylon hanging gardens, and there are historical proofs are not that much concrete, but people are finding out some details. So when you think of that kind of structure, where we have the plants at a very high level, where the people, if you go or bring the water, this very tedious job. So initially maybe it's possible, but for entire kind of span, that may be very less, unless you have a very strong army of men there working on that. So it is possible. At the same time, if someone is intelligent enough, that how it is possible using the kind of laser labor. So when people start thinking about those, they just formalize these theories. Like if you think of Archimedes, if you think of Leonardo da Vinci, if you think of Euler, if you think of Navier-Stokes, they started to find out something new, something that may uh, found from their own knowledge, and try to push whatever the present thing to the future. So something new is was added. So what my point is that if they could add something and that was out of concept, so why we should not put more importance to clearing the concept, not just putting into the formula. There are so many softwares nowadays available, the mobile apps, so you can calculate any kind of engineering parameters that can be used in different streams or different sectors, different problems. But to decide that which formula should we use in a particular problem, that decision should come from out of the knowledge, not just remembering the theories. So that knowledge development definitely takes through the experience. It takes time to grow. But when you talk about going back to the basic to find out solutions, we have to somehow merge that kind of experience, that kind of exposures into the teaching, and that is very important nowadays. Let me just brief about my journey about this learning the theories and trying to solve the problem for the planet, because I dreamed about this problems for the planet kind of 20 years plus ago. So it was 1999 and I was in 11th standard. So there I found that the Kyoto Protocol was important for the planet to reduce its emissions, but it was not validated by some of the countries who are the big polluters. So what we can do? So being a common man, just a student, you don't have anything to do basically. So what is the power that you can have? Maybe you can have, or you can go for the activity, become the activist. You can just put something on the streets. You can put nowadays. You can put something on the online. You can petition. You can do something to make that voice clear. But when you think about as a student, you have the more opportunity to gain the power through the knowledge. So I took that route and I actually made a lot of experienced people in that field, in the environmental field, who were working on that point that we should do something for the planet. So I started looking beyond the syllabus. Definitely, I get some feedback, and then I come back to the syllabus. I see that what we should put the importance. What part of the kind of standard curriculum that is important to understand the current situation and find out more practical solutions. So I thought that either chemical or civil engineering was maybe better for understanding the technical part, because I had some technical background from my ancestors. So that why I choose civil engineering, and then I put more importance to the basic theories, fluid mechanics, then engineering designs, then hydrology, environmental engineering, and the pollution control. So these were the subjects that I definitely liked and tried to grasp as much as possible. And definitely, I had to run outside the class, catch the teacher, and get what I can get the most. Because definitely, always this curriculum teaching is very restricted with time. So we have to utilize that with kind of uh, your own quest. So you have to make some more time out of the teacher. You can utilize his or her knowledge so that you can get more. So in that quest, I continued to the master's level of, at IIT Bombay, and there also I was exposed to a lot of practical problems, and those are related to environmental engineering. So that definitely challenged me that how can we learn all these things? And all the time when you solve a practical problem, there's some part that you may not know even. So, what to start with to understand the problem, understand those big kind of handbooks or the reports. So, always I try to go back to the basics. That from basic engineering or basic science, where we can start with. Maybe you can have to read some part of the physics or some part of the chemistry or maybe some part of the mathematics that will help you to understand the things. And then beyond that, that is a logic. So we have to utilize those kind of tricky things to look into the problems and create solutions. So every time basics was my target that I should get a strong out of this. And so that I also decided to go for the PhD, and that PhD I started in US, but it was never ended there. And then I finished off in India, that is in IIT Kharagpur, and I was fortunate to have those kind of peer guidance that helped me to connect to the very basic statistics, probability, and the hydrological science, where we can find out the links from those basic to create a very kind of innovative solution that no one else basically developed. So that's how the publications came. And then I started thinking what next. So when you understand the climate change, you should have to look into the hydrological science. And just going through my doctoral work, I understand that the monitoring, modeling work are very much there. The people are doing that for a long time, and that is mostly from the hydrological side. But I have basically the masters in environmental engineering. So where those links, where I can utilize my knowledge in dealing with the practical problems of the environmental engineering with the basic training that I got from my doctoral research. So then I found that is the environmental hydraulics or the kind of overall this is the climate dynamics with uh, the part of the hydraulics that may be very much crucial. So that's why I propose a kind of project to the DST, and I got the Inspire Faculty Award on that. And then we started working on that ABL, that atmospheric boundary layer. I have worked basically on pollution, different kind of pollutions. It's not only the air pollution, but also water, solids, e-waste, and as well as some sort of noise pollution, ecological deteriorations. So all these things that was in my back of the mind, and then I thought that what I found the approach that to link from the basic to these problems that should be utilized. So that's why this ABL, the atmosphere boundary layer problem, came into mind, and I wrote that project, and it was sanctioned by DST expert committee. So that I started at IIT Roorkee. But just after my doctoral, I was there for almost 8 months in NIT Sikkim. So it was a lab of the Himalayas, and there I saw that how the nature can be mingled with our lifestyle, how nature is very close to our lifestyle. Definitely, we have the engineering system, we have the public works develop department, we have the electricity, everything we need. But definitely, we also need the nature. It's not about just having some kind of leisure time, but it's also required that if we find out the link with the nature, and beyond that what we generally think of, like a forest, we maintain a forest, we maintain a park, or we maintain a river, but from the basic understanding of the natural things, that is very good for not only for kind of our health, but also kind of good for when you try to solve a big problem, and that is nowadays mostly related to the climate and kind of natural entities. So that is basically required, but definitely that sense was not very much kind of implemented because of some restrictions. So with that, I came to Roorkee, IIT Roorkee, and I started working on that simulation. But the simulation is one part that definitely we have to do. We have to understand the problem. We have to understand the theories where we can maybe we can use the finite difference method or finite element method. Finite element method basically we use in the mechanics, and finite difference we are very much used in the climate related or hydraulics related problems, and that we develop some models that is basically partly very classical science of hydraulics, but partly it is more applications toward the air pollution meteorology. So in those cases also, definitely we have to every time we have to go back to the basics. We have to understand the theory of the fluids. We have to understand the fluid mechanics. We have to understand the finite difference method. So all the basics again come back to you, and when you try to solve a problem. So in that case, we also develop a few models. Sometimes we have combined with the classical model with the very much applied models, and then we started doing the publications. But the publications basically was not the kind of chapter of the whole story. So we had to make a kind of complete story that I was looking for long, and that basically not just understanding the problem. That definitely it helps when you do the monitoring or modeling. It helps you understand the problem. You help to understand what the situation is, how the natural process is going on, what changes it can happen, maybe for the present, for the near future, or distance future, if you have kind of reliable mathematical models. So we can do that, but it does not gives you the direct solution. And solution means it's not just always a kind of big large solution, maybe a dam or rebuilding the dam or restructuring the water resource, planning management. All those are possible, but not everything possible for me and not everything possible for individual. So what I have the experience, I want to utilize that in creating those solutions. So that's why we started a little bit of composting, little bit of looking into the real problems of the environment. Maybe it's that burning the leaves or crop waste. That was a very big issues, definitely in the winter, mostly in the northern side or north western side of India. So there are a lot of crops they grow, and after the wheat, there is a kind of few months gap. But in that time, we get a lot of rain due to the western disturbances. So the farmers thought of why not utilize that kind of window where you can grow a particular crop, that is maybe paddy, between this standard Rabi and Kharif seasons. So that's how the paddy cultivation started in those regions. But the problem is, like, you don't have enough time to take out those roots of the old wheat plants, and then people start looking for the very cheaper solutions, and they start burning it. And when it burns, there is a kind of stabilized atmospheric condition that happens in the winters, and that is because of the less thermal gradient that we generally find from the surface to the above. So because the less area is exposed to the sunlight, the temperature is low, so all these basically put the things in a certain stabilized atmospheric condition, and that means actually that there is not much wind, not much movement of the particles inside the whole area. You definitely think of the three-dimensional form. This is you can think of the whole region as a area, and particularly where up to level that where you can get these pollutant mixed. We call it the mixing height. So within that whole three-dimensional area, if the particles started move slowly, so definitely where the pollutants are getting generated, that is definitely the surface, that will not move away further, and that definitely creating more nuisance, because that particles is basically creating PMs, the particular matter that we generally get trouble with. We have the PM 2.5 or PM 10 in micron size, and more the sizes are smaller, even PM 1 micron. That is also very much harmful, but it's difficult to measure. So PM 2.5 is generally a kind of indicator of the whole pollution scenario, and that actually penetrates to your lungs. And when it penetrates to your lungs, definitely it creates some disease, some deposition happens, and that helps you develop the toxicity inside your own lungs. Breathing problems and other problems definitely come into picture. So we are not going in that direction, but since this kind of stabilized condition that we already found from our research of the ABL, the atmospheric boundary layer, and boundary layer that is basically the lowermost part of the whole atmosphere. So we have to look for some solution. The monitoring modeling definitely give you kind of understanding that how it happens, what is happening there. Now, if you stop there, academically you're fine. You can get promotion. You can kind of please your funding agencies. You can kind of tell the publications that we have done some work, we have published book, we have published papers, but that does not give you the satisfaction from inside when you are basically out to look, kind of looking for a practical or sustainable solution. So out of that quest, we also started the composting things, and we also utilize whatever I have the knowledge from my doctoral work that is on the soil moisture. That if we can kind of retaining more soil moisture in a particular area, that also helps in the fertility and the growth of the plants. So when that is important, so why not we kind of decompose what are the plant roots are there, the crop roots are there, and that if we able to mix it with the soil, that will definitely help in the retention, the water retention that we already know if you studied the soil mechanics, and so that is very much common that the water particles get trapped within the pores of the soil, and that remain there until there is a gravitational force, or there's some kind of hydrostatic pressure that builds up. So that is very much important to in the top layer, maybe around 10 centimeter to 1 meter for different crops. So what we try to find out that if we do composting and if we disintegrate the fibers of the crops to certain extent, and that basically kind of helps the moisture or the water particles to retain more inside the soil. So that's the solution we trying to find out. But there was a practical issue. It's not the lab case that we are going to do because this is an open field, and there's a field not just a few meters square, but it is a acre. So when we talk about the physical application of those fields, we have the challenges for space as well as the time. Space wise, there's a large area, so if you want to cover with kind of walking or labor, it is sometimes difficult. So there's also harvesters, some kind of extra prop that we use with our tractors, and that helps to mingle the kind of crops with the soil. That is fine, but unless those crops are getting composted, that won't help because the fibers are still strong and they are combined, so they don't won't help in compost kind of retaining the soil moisture. So what we were working on lastly, that is that how we can develop some kind of microorganisms. They actually not only compose the this crop waste, but also stick to this in the field. So in the lab scale, on the pilot scale, we can use an enclosure that is very easy and that can be done in a controlled manner. But when you talk about the open field, even the hydraulics, the water flow, the flow of the wind, all those come into the picture, and that is a different game. And but that is only the part of the story because we are talking about space, that is acres, but we also another restriction that is about the time. So when the the wheat crop is end and the paddy starts harvesting or harvesting of the wheat and the sowing seed or the small saplings of the paddy, there's only 15 days gap. And if you look for the standard composting techniques, that is basically kind of takes about 4 to 5 weeks. Some techniques takes 6 to 8 weeks. So we have the time restrictions also. So when we are started thinking about that, we use some based on some previous research. We started developing some kind of fungi that may be combined with some genetically modified organism that can stick to the surface, and we can use it very easily, just spraying over it. And when it sticks, and it can degrade the lignin to some percentage. It's not the 100% degradation we can achieve within 15 days, but we have found at least 60 to 70% degradation was there uh, using those microorganisms, and that can be used as a kind of supplement of the fertilizer that we generally use in the field. So in one case, one side you can stop burning and utilize the what are the best part of the nature that you already there in the field, and then it will also enhance the retention capacity. It also enhance the soil water retention. It also enhance the fertility of the soil, and definitely the successive crops that also get the benefit of this. So that was kind of toward the solutions. And to make these solutions toward the large scale, that was kind of next step that I try to follow. And there also definitely we have to go back to the fluid mechanics. And what we I found that people have started working on the hydroponics and the aeroponics or aquaponics. These are nothing but the cultivating of the crops with the water only. And as you know that we have the issues of soil contamination everywhere because we have been using this chemical fertilizers for long. And over these years, what happened that these fertilizers, most of them, they get washed away from your field to the another field or the water nearby water bodies deposit there, and wherever it deposit, it not only kind of change the whatever the ecological formation of those strata, but also degrade itself, and in between the what are the mid portion of the degradation. So that also creates some problem that sometimes become very toxic to this soil. Some microorganisms can not survive in those situations, so soil are getting contaminated. So what was the kind of option that we could bring to have a better food? Because ultimately we have to eat better things, we have to live better, and that also we have to save nature. So if you think of the supply of the food thing is very large quantity that we use, that we used to do every time, but not only just the soil contamination but also the temperature fluctuations, the uh, rainfall deviations from the average, that is creating problems to the agriculture. So that's how the agriculture become more focus sector for my research. And then I thought of that why we can't develop certain hydroponics where since we are using the hydroponics, we have to supply the fertilizers, and if we can develop a kind of good system that you get the fertilizer out of the crops itself. So that actually combines the circle. So when you talk about the fluid system, we also think of the mass conservation. We also think of the continuity equation. We also think of the circulation, recirculations. So in that line, why we can't have these kind of system where you do the all recycling inside the whole system without taking much outside help, and that you make it self-sufficient. So the fluid become another action in this system where we combine the composting with the hydroponic system. And as you know that there are many such systems are there. Hydroponics, also aquaponics. Hydroponics is basically just grow only the crops with the water. And when you talk about the aeroponics, you have to just spray the water and grow the crops. And when you talk about the aquaponics, is basically the growing crops as well as the fish together in a recycled manner in the same system. So here also we have another opportunity to add more nutrients. One way it is coming from the crops, but if you think of the whole mass conservation side, that what we utilize for the composting things, that is kind of residue of the entire crops. So we already reduce the mass, so definitely we need some more supplements when we talk about the nutrients, uh, quantity, the concentration, etc. in the whole system. So we need some supplement. So why we cannot use the fishes, where the fish excreta basically are very rich in the nitrogen, phosphorus, and potassium. Those are basically the basic ingredients in the fertilizers. So in that sense, we try to develop certain filtration. Since I have the environmental engineering background, where we definitely study the photochemical, the physiochemical reactions, uh, treatment plants, filtering, the osmosis, reverse osmosis, uh, gravity filtration. So we can develop a filter. But why a filter required? Because what we have in the fish excreta, that is basically the rich in nitrogen, and nitrogen in the form of ammonia. So when it is a form of ammonia, it has those ions, the plus H plus ions, and that is not good for fishes as well as the plants, because they are very reactive and they does not get absorbed. So we have to convert the ammonia to certain form of the nitrogen, that may be nitrous oxide or nitrates. Nitrates is the best kind of one of the best fertilizer we used to have in this crop fields. So if we can convert that ammonia laden excreta, the fish excreta, to the nitrate, that definitely helps in supplementing the whatever the nutrients required by the plants from the composting. So if we do that, we have to filter it. We have to do the biofiltration, where we can convert the ammonia to the nitrite, and then nitrite to the nitrate. So nitrobacters and all those we have to bring in and do some kind of natural processing. And here also the flow or the fluid mechanics again play a very important role, because all are passing through the waters. The water basically carries all those particles to certain places. So you need to separate the solid particles from your fish tank, You have to capture them and you have to put them in the filter. And then again from the filter, you should not take the uh, solids, but you should take whatever the nitrate or converted nitrogenous oxides that should go to your plant tank. So, what are the volume or what are the flow rate that we have to decide? You have to go back again to the basic part, that is the fluid mechanics, that is the continuity equation or the momentum equations. Every time when you develop the same thing, so that's why this fluid mechanics is very important for us. And maybe when we study this subject the first time, the first years in the engineering, they may not realize in the same time. But when they sit for the competitive exams or try to develop some new stuff, nowadays a lot of competitions are there. Either they develop apps or they develop some innovative systems. Always the basics are the best tool that they can have. But definitely the experience may not be there. The enthusiasm is there, but experience is sometimes lacks, and that's why they take help from the teachers. And we have kind of those courses, the research problem based courses are there in the IITs. So that helps the student to kind of take the advice from the experienced people to develop certain new things. But always the knowledge or the basics that is handy, that helps you to understand that what we should start with and what is the direction, what should direction we go. Nowadays, the it is kind of open book world. And when you started, the internet was very kind of basic things. It has developed over the 20 years, and we have apps, we have whole knowledge is on the open area. Nobody actually bounded by the institutes. They can search anything, they can do their own system. Even if you just search on the YouTube, you can find out that people or the students in Africa, they just exposed to the internet little bit, but they are developing very good system that is very innovative and also very kind of connected to the basics. So anybody can do anything, sitting any location around the planet. But the thing is that unless you have the basic quest, unless you know the basics, unless you have the kind of quest that you should have to develop, you should do this. And I know this very much, I'm confident about this subject. That whole dream may not become practical, or you may not come with this kind of make it realize. So that's why theory is very important. And who are the practitioners who are already there in the industries, and they already have the handbooks? They use handbooks to just find out some formula, some devices they have creating problems in your industrial setup. Somebody has a problem with the control system, and you have a kind of oil refinery, or you have the water treatment plants. So everywhere the control systems or the day-to-day activities that challenges your knowledge, that you have that particular sense, particular theory that you already maybe studied in your college or in your schools, that how to apply that, where to apply that. And definitely there are many handbooks that are available nowadays. There are a lot of online calculators are available, but unless you are very much confident about that concept, that what is behind that particular formula, there is there is no use of those theories. So that's how these kind of courses very much required for all of you who are interested, and that's how I try to tell in different manner. You can hear the sound, you can hear the ambience of telling stories, and sometimes you will also get some equations, uh, very basic equations that we know from the fluids, from the properties of the fluids, from the statics, from the dynamics. Uh, Definitely, you can remember the continuity equation. You can remember the momentum equation. You can remember the energy equations. But just remembering the formula, that also does not help you when you are trying to apply that, because there are some assumptions, there are some concept that where you can use that. You should know that background, you should know the story behind the formula. So that's why I try to kind of design this courses to tell you the stories, tell you some kind of interesting part of those theories, those assumptions, those hypotheses, and also we'll derive some large equations like Reynolds average, Navier-Stokes from very basic three-dimensional flow equations, step by step, with assumptions and with the practical applications. So when you combine those points of applications with the point of studying the theory, that definitely give you a kind of extra interest that someday either me or some of your known people will going to use that, and that helps you to solve the problem. So in that view, I'm trying to develop the entire green engineering curriculum, because I have developed some curriculum while I was in NIT Sikkim. We revised the entire curriculum, and I was also fortunate to have kind of future curriculum of civil engineering when I started the civil engineering program. Just before that, somehow I got it. I don't remember exactly from what is the source. It was mostly in the newspaper somewhere, and I put it down in a notebook, and then I try to follow that. So nowadays the competitions are also getting tough. Like if you apply for a job, or if you apply for some higher positions, if you go for the competitive exams, so everywhere just putting down everything in the mind without understanding, without capturing the essence, without capturing the story, is very difficult for you to excel. So that's how these things are here. And green engineering curriculum is about preparing the students for the future. So students definitely follow standard curriculum in their schools, in their colleges, or the higher universities. But there's something is going on in the practical field, and that is moving very fast. Every year, the climate is changing faster and faster, and definitely people are started studying that. People trying to find solutions, but recent reports are telling kind of bleak stories about what we are still doing, because till we started the sustainable development concept, we have not followed the sustainability in our own life. So that maybe the what are the strategies we have, the business strategies, what are the development strategies that we are doing, that is not at that pace where we should go with. So in that pace, that may not be sometimes possible for the academic people, but it is needed for the industrial people, it is needed for the businessmen, it is needed for the administrative people, so that they can make a good decision. They can take a good decision at that point of time, which will be kind of more visionary and more applicable, and also based on more basics. So that's why this green engineering, this is I'm trying to cover not only the engineering courses, but some of the related art, science, commerce courses. And I'm also open for the collaboration for this curriculum around the world. Wherever people are interested, they can come with me and teach some of these courses. We can co-develop this, and engineering part, all the basics I can teach. Fortunately, for just go through my entire academic career, I have to learn lot many courses that people generally have. Like I have done environmental planning, I have done course in the toxicology and engineering designs. So that give me more confidence about taking up some of the engineering courses that may not be very much usual or standard in the civil engineering or the architectural sciences. So that we trying to cover, because the green engineering is not about just civil engineering or the chemical engineering or the mechanical engineering. Is the engineering is the kind of intelligence way to solve the problem for the planet, because the planet have lot more issues than we see today, and some of the issues we already saw, but we are not able to solve it. So to do that, we have to come up with some uh, intelligence that will definitely help us to find out those solutions. And I personally believe that from the 11th standard onwards, we have the enough capability or knowledge or the kind of brain growth that we start capturing this essence of green engineering. So that's why this green engineering will start from the 11th standard. Some of the basic courses will start from them. And first year of this green engineering is suitable for the 11th and 12th standard. Then 3 years for the bachelor courses that will develop all the engineering basics things, and then more application oriented courses or deep research courses for masters and doctoral student for the last year. So this is the overall framework that is already there in the post of my LinkedIn profile. So anybody can look after that, and also that will be available on this YouTube channel. And hopefully all of you enjoy a little bit of stories. I didn't use that this whiteboard, right? I didn't, because I will start doing that from the next class. Today is just an introduction, and for some issues in the YouTube, I could not go live. But definitely, we can start having the live streaming from the next class onwards, and there we can interact with the students wherever possible, and we'll continue to tell you the story so that everybody will catch the theory to solve the problem. Okay, so stay healthy, stay alive, focus on your work, and we'll come back to the next class. Thank you. Bye bye.